Hello everyone and welcome to our course Climate Hazards and Disaster Mitigation. Today we are going to discuss hydroclimatic measurements and data. So what have we learned so far? We understood the terminologies of hazard, disaster, risk and vulnerability. We also discussed what are the causes and impacts of climate change and their role in formulating or escalating climate hazards, and we also appraised the risk and vulnerability profile of India. So for today's lecture, our learning objectives are: we'll understand the hydroclimatic measurements and the data for climate hazard and disaster mitigation studies. We'll appraise various data types and their characteristics. We'll understand the difference between the data types and their usefulness in hydrologic studies. And lastly, we'll explore the data sources and their availability for key hydroclimatic variables. To begin with, we should understand what are hydroclimatic measurements. So in very naive language, they are the data which are used to study the interaction between climate and water on Earth. These will include several variables like precipitation, temperature, wind, storm surge and stream flow. These measurements are usually used to monitor systems, assess trends, analyze extreme events like floods and droughts, as well as model climate change impacts. Specific examples would include like getting data from a rain gauge to measure precipitation, satellite altimetry for water levels, soil moisture sensors to quantify the movement of water in the ground. So hydroclimatic data has very crucial applications. For our case, we'll be mainly focusing on the climate hazards. Now, what is the need for measurement? If we have these measurements particularly long term, then we can go for proper planning, we can design, we can manage the systems, and we can even do extensive research on various parameters. So coming to the data types, there are 5 major data types. To begin with, there is in situ data, which is also called point data, which we get from direct measurements from sensors and observation stations. Next is remote sensing products, where the data is retrieved from the satellite and other remote sensing technologies. Drone is also one of them. Then we have gridded observational data, where your data is aggregated or it is interpolated in a uniform spatial grid that facilitates analysis. Then we have reanalysis data. Now it is a more systematic and homogeneous data set, which includes historical information by combining the weather observations and you have using some data assimilation system or models. So they are kind of simulating various scenarios to come up with a more homogenized data set. And lastly, we have the gridded projected data. These data are created by combining past observations. Now whether it could be a ground based or satellite based observation, but past observations coupled with some climate models to provide consistent high resolution data, usually for projecting future conditions under various scenarios. So beginning with the in situ data, so these are collected by the ground based seaborne or airborne monitoring systems. These data is very critical for calibration and validation of other data types like satellite data. For example, we are getting some precipitation from a satellite data, but the thing is there can be some errors as well. So we have to validate those data, and that is where this in situ data is very critical, because in situ data stands as a firm validation set against all these data. What are the examples? So you have precipitation. So precipitation is one of those variables which we get. Then you have soil moisture. There are many ground based sensors which we get. Then water levels and discharge. So we have stream gauges or monitoring wells where we can measure water level and discharge. Water quality data can be again retrieved by in situ measurements, where physical and biological parameters of water which we can extract. And then you have meteorological variables, where we have a weather station mounted on which we can measure air temperature, wind speed, relative humidity, atmospheric pressure and other details. Now the very basic data which is of preliminary use, that is our rain gauge, that is the rainfall data we get from a rain gauge. So there it can be either a Siemens type rain gauge, which is a non-recording type, or it can be recording type like tipping bucket, weighing bucket, or natural siphon or float type. So in India, IMD, that is India Meteorological Department, is the primary custodian of the rainfall data. Of course, apart from that, there are state agencies and sometimes private owned and other data, but IMD is the main provider of these data. What are the advantages of in situ data? That it is having high accuracy because it is a point observation. The second characteristic is that you can get particularly long data because some of our IMD stations have started well in the 19th century. So you may have at least 150 years of data, and the only limitation is that it does not capture the spatial variability very well. In some areas where because as a general thumb rule, in hilly areas the density of rain gauge should be very high, but at some areas we will see further that the density is not as expected, and that is where this thing can be a lacuna. So looking at the IMD rain gauge networks, so there is total 6,955 rain gauge stations available all across India. Out of that, 547 belong to IMD observatory stations. Then there are different categories of IMD stations. Then there are hydrometeorological stations. Then you have agromet observatories. So all these aggregate. Apart from that, there are some stations which are operated by the state governments as well, but come under the IMD fold as well. So if you look the spatial distribution, here you can see in parts of Rajasthan and Gujarat, you can see that the rain gauges are very sparse. Again, if you see the northern part, Jammu Kashmir, Ladakh, very few rain gauges. But comparatively, if you see this part, that is the Western Ghats and this Karnataka, Tamil Nadu region, East Coast region of Bihar, they are very densely gauged. Again, if you go to the northeast region, again the gauge density is very sparse. So these regions may face some issues while you are utilizing this data for various purposes, but where the density is particularly high, this is a very accurate data set. Now let us look in what format we get. So from IMD, if you get the rain gauge, that is from manual. So this is the metadata it will have. So this metadata will include what are the data type, then this is the station name, in which district it is, then you have the catchment number, that is the IMD denotion, then you have the lat long. So all this information is available, and then this column is the year, then you have month. So these two are represented on the rows, and on the columns represent the days. So each month has 31 days, so where the days are not there, so this will show a blank. So this is in .txt format, and from this you can convert into any format. Maybe you can convert to .csv or other formats. So like that, you have a continuous long-term record available from the rain gauges. Moving ahead, then second type is SRRG, where you have self-recording rain gauge. In self-recording rain gauge, again your metadata shows what are these abbreviations. So HRF stands for hourly rainfall. So this is the station index, which is shown here in the first column. Then you have year, month and date. So these are the information available in the rows, and your columns will include the rainfall from first hour to 24th hour in a day. So it will be at hourly interval. Then here you have some stats like what is maximum rainfall and other things, but we are interested in what is the rainfall from 1 to 24 hours. Now coming to the remote sensing data products, that is the next category. So in this remote sensing data products are output from satellite and airborne sensors that provide quality spatial and temporal information about Earth's surface, atmosphere and oceans. These products may include raw and processed data such as optical and radar images, sea and land surface temperatures, greenhouse gases, ocean current forecasts, land cover maps and variety of those. Types of this data are satellite and aerial imagery, oceanographic and land atmospheric processes. So moving further, we'll give some examples of the remote sensing products. So this is one such precipitation product, that is Persian CDR. So that is available at a spatial resolution of 0.25 degree, where the extent it covers is 60 degree south to 60 degree north and 0 to 360 degree longitude. Next we have is another precipitation product, that is TRMM, which is known as Tropical Rainfall Measuring Mission. So again, it is a gridded format, it is available, but from a remote sensing observation. Then we have remote sensing product for sea surface temperature, so that is available from NOAA. So it is a reconstructed sea surface temperature which is available. Then we have another sea surface temperature product that is from Copernicus EU. So these are the some of the examples which we shared about the remote sensing products. Now coming to the gridded data. So gridded data provides a spatially continuous coverage over a defined area by dividing into regular grids of cells. The value at each grid cells is an estimate of the average condition within that area. So for example, if I have this particular area and I divide it into some equal rectangular grids. So each grid point, that is a combination of a given longitude and a latitude. So I can represent, for example, this particular grid can be 15 degree north and 20.5 degree east. So that way each grid point can be represented, and these are the grid points which are falling in a particular area. Now how this data is formed? So in a particular area I can have certain observations which may be irregularly spaced, and using some interpolation technique, then these observations are converted into grids. So that is why it is called the estimate of an average condition, because they are averaged spatially. This format is widely used in hydrological modeling, climate change studies, because it offers a complete spatial coverage and it makes your data more uniform. So let us look, the example is IMD gridded rainfall data. So in the earlier slides we showed the distribution of rain gauge stations. So using that they have interpolated it to come out with the gridded data. So earlier the IMD had a gridded data at 1 degree, then it made it more finer resolution 0.5. Now the latest is available as 0.25 degree. So that roughly covers around 25 by 25 kilometer square area. So the only disadvantage is that sometimes, because you tend to spatially average things, so some extremes may get averaged out, but the other the chief advantage is that in the station data there are a lot of missing values. So here since it is using so many observations, so that inconsistency can be clubbed up. So IMD provides gridded rainfall data. So on an annual basis you can get this data from the IMD website. So all the metadata and information is written here. Now if you have the rainfall data, then you can just see what are the variations of rainfall. So this is a map which is showing the global precipitation variations. So you can see that this region receives very low rainfall as indicated here, and there are regions here particularly receiving very high annual rainfall. So the rainfall distribution can be determined. Now before moving ahead, we should understand why and what period of rainfall to be studied, because particularly in India, if you talk about the monsoon rainfall, there are two principal seasons. That is, one is a southwest monsoon, which is the very predominant monsoon season, where around 70 to 80% of rainfall is received in that season. And the second is the northeast monsoon, where around 15 to 20% of rainfall is received in the northeast monsoon. Now southwest monsoon, it starts setting by late of May or early of June. So from Kerala it will start setting. So that is our first branch, which is the Arabian Sea branch, and the Bay of Bengal branch. So there are a second branch which will come somewhere from this northeast, and both these branches will converge in North India after progressing 30 or 35 days. Now as the winds hit the Western Ghats here, this region receives more rainfall. Similarly your northeast India, where Cherrapunji and Mawsynram, they also receive very high rainfall, so their orographic effects is more predominant. In north we have the Himalaya, which acts as a barrier, and our northern plains also get more rainfall. In contrast, your northeast monsoon, northeast monsoon is most predominantly influencing the eastern coast of India, that is particularly Tamil Nadu, Andhra Pradesh, Odisha. So these regions are more influenced by northeast monsoon. It is shorter compared to southwest monsoon, less widespread, but important particularly for southern India, because many a times you may hear that Chennai is getting floods in December or that season. That is particularly due to the northeast monsoon. If we see rainfall distribution in India, the average rainfall is around 118 centimeters, while the western part of Rajasthan receives very scanty rainfall, while the parts of Western Ghat and the eastern India receives the highest rainfall across India. So we can see wide spatio-temporal variability is observed in rainfall. Now IMD website, if you scroll through, you will get all the parameters. You can get district wise information, state wise, meteorological subdivision wise, river basin wise, all this information. So here we are just showing what all values you can information you can retrieve. That is, this is a cumulative rainfall in last 24 hours, which are converted into various categorical variables. Then you can get information about the satellite image, so you can see how the clouds are progressing, that is also available. From radar also you can get information where the rain is concentrated. Then you can also get information about lightning and thunder. So IMD provides a wide variety of information. Again, you can get what is the actual rainfall that occurred, then what is the normal rainfall for that particular date, and what is the anomaly based on the data. So lot of information and real-time information is available on the IMD website pertaining to this. Looking at some characteristics of selected rainfall data, that is graded rainfall data. So if we see that this is taken from a study, Paul et al. So you can see that IMD graded data classifies as an observational data because it is prepared from an observational data. There is an Aphrodite data, so the spatial resolution and temporal resolution and the period of availability is also mentioned here. And then we come to reanalysis data. So we have IMD AA. So in the later slides we'll see what are these data sets. You have ERA 5, PGF, then satellite data and hybrid. So these are four major categories of data which are classified. Their spatial, temporal resolution and their availability is given. Now why it is important that if you have multiple data sets, then you can compare that which one is more closely aligning to your observed data set, either from your satellite, reanalysis or hybrid data set, and that can be used as a proxy for in case of missing observations or other applications. Coming to temperature data, so IMD measures again daily temperature using method that sums maximum and minimum temperature, and then it gives the average temperature value. It also gives the maximum and minimum temperature. So it records air temperature at various weather stations. Some of them are manual, but now there are automatic sensor based stations also which are there. So apart from that, there are some hydrometeorological observatories which will also provide you the dry bulb temperature as well as the wet bulb temperature. So these are useful in calculating the humidity. So usually we'll get values in degrees Celsius. So again, IMD website will provide you the temperature data. Compared to rainfall data, the spatial resolution of temperature data is 1 degree by 1 degree. Rainfall is at much finer resolution, but temperature is at 1 degree by 1 degree because there is not much variability in the temperature data set. So you get two variables. One you get T max and second you get T min. So similar to rainfall, IMD website also provides temperature visualizing the temperature data as well. Next comes reanalysis data. So now reanalysis data is a collection of historical weather and climate information which is created by rerunning past observation through a fixed model. Now this process combines whatever all historical information you have, or it collates data from satellite, weather stations, ships, buoys, etc., and then it has a numerical model which will generate dynamically consistent graded data. Now why this is important? Because you get a consistent time series of several weather and climate variables, and that overcomes the limitations with the incomplete observation networks. What are the examples? If we see in atmospheric variables, you get precipitation, you get air temperature, you get wind, you get pressure, and humidity and other variables. Surface and land variables, the primary are soil temperature, soil moisture. In vegetation, you get leaf area index, albedo, you get evapotranspiration. Then in water, you get evaporation rate, runoff, and other parameters. Oceanic variables, you get sea surface temperature, salinity, and sea level pressure, and other variables. So these are available from the reanalysis data set. So one such reanalysis data set, this is an Indian data set, that is IMDAA, which is Indian Monsoon Data Assimilation and Analysis. So it is available at a very high resolution of 12 kilometer at hourly time interval from 1979 till 2018. So that is where the data is available. We have another one, that is ERA 5 land, that is a European reanalysis data. So it is again available at a comparable resolution 0.1 by 0.1 degree, 1 hourly, and the time period is much longer from 1950 till present. So these are the some reanalysis data sets which are available. Coming next to the gridded projected data set. Now the word projection implies that we are looking at a distance time frame, so maybe some future horizons. So these are collections of scientific data which are again in a gridded format, and which contains future projected values of several climate or weather variables or population variables or some socio-economic data. So these are obtained by combining or interpolating data from multiple sources or generating outputs from models like GCMs and RCMs, that is global circulation models or regional climate models. So from there also we can get it. The usefulness of this projected data set is that we can use it for studying what are the long-term variations or future changes that can be anticipated, and based on that future trends can be discerned. So again we have climate and weather data, that is the first category, where we have precipitation, air temperature, potential evapotranspiration, and other variables also we get from the GCM, RCM models. And there are socio-economic and earth science data where you can get projected population, what is a gross domestic product, that is GDP, land cover, and other variables also we can get from the projections. So one such is CMIP 6, that is coupled model intercomparison project phase 6. So these CMIP 6 is a suite which contains lot of GCM models. So you can see some of the GCM models are listed here. Each model considers various forcings and constraints into their into their nomenclature, and then they come up with lot of versions of the data and for various scenarios. So right now in CMIP 6 models we have 5 scenarios. So we have the first one is their historical. So that is the historical simulation of past observation till 2014. So how the past climate is behaving. Then we go into future from 2015 onwards till 2100, where SSP 126 will give you a sustainability or low emission scenario. SSP 245 will give you intermediate emission scenario. SSP 370 will give you your high emission scenario, and SSP 585 will give you very high emission scenario. That is, our entire economy or everything is fully fueled by the fossils. So that is how these scenarios are derived, and based on that you get projections for different scenarios or trajectories. So this data is available in .nc format. So these files are called netcdf files. So from that again you can extract it into .csv or any other data format, and you can further analyze it. Another gridded projected data set is population. So from NASA Earth data we get gridded population of world, that is GPW data, that is high resolution population data where you get population projections for the entire globe. Apart from these, there are other data sets which are which do not qualify in these categories. So one such data set is CAMELS IND. Now this is CAMELS data set that is providing information on the catchment attributes and meteorology for large sample studies. So this is an Indian version. It started with CAMELS US, and there are other versions as well. So in CAML's India data set, so we have time series of hydrometeorological variables, including stream flow and precipitation, temperature, PET, and the catchment attributes like what is the catchment area, what is the slope, what is the soil type, and other parameters for 472 catchments in peninsular India. So we have a very large database. It is covering a very large area, and I think the period is from 1980 to 2020. So that is a very good data sets which can be used in combination with the earlier data sets. Coming to the next important variable, that is stream flow. So stream flow is usually measured using several techniques. There are a lot of advancements in stream flow measurements coming from the traditional current meter to then staff measurement, that is measuring water level and converting it into discharge. Now you have automatic sensors, you have laser Doppler velocimeters, and so on. So there is a lot of advancement in stream flow measurement have taken place. Now why it is important? Because stream flow is one such component of your water cycle which can be accurately measured. Also you get a know-how of the entire water cycle, what is a water quality, also how the ecosystems are behaving, and ultimately we can manage our water resources. So prominent source for stream flow data, that is India WRIS, that is Water Resource Information Systems. So if you go to the website of India WRIS, you can get time series of this data, particularly for the peninsular Indian catchments. So you can access the portal, looks something like this, where you have the metadata of the station, station name, which agency is disseminating the data, which river basin or river it is, what is the data length, whether the station is active or not, lat long, and all the metadata information you will have. Then you can download the data for the selected period, and then you can enter your email, and then the data will be shared on the email. So you have this metadata in this particular sheet, and in this sheet you will have the discharge value. You can also get the water levels, so all that data can be collated. Next is a variable, that is wind. So wind is a very important variable, particularly in air pollution studies, particularly when you are studying cyclone movements and its effect on the structures, etc. So wind becomes a very important variable. So in wind there is a Beaufort scale. So it was developed for initially to be used for sea navigation, but later it was adapted for in terrestrial systems as well. So wind data, we have wind data which can be secured from NOAA. So again it is a gridded format data. So from NOAA you can get the wind data. If we see the India wind map, so this is the scale where you can see. So this shows a very high wind intensity. So you can see the southern part of the India. Then there are parts in the western and part of India, and here in the northern part. So these regions receive very strong winds. And why it is important? If you want to harvest this wind energy, then if you set up plants in these areas, then you can get maximum potential utilization of that. Further, your coastal areas fairly receive higher winds because of the sea breeze which are coming as compared to the inland areas. The next variable, that is the storm surge. It is particularly important when you are talking about coastal floods. So storm surge refers to an abnormal rise in the water level which is above the predicted astronomical tide. So you have an astronomical tide, so which is of a defined magnitude, and above that whatever is the water level which is observed, that is called the storm surge, because you have this mean sea level and your tide will fluctuate between the mean sea level, that is high and lower tide. So storm surge is over and above that. So usually cyclones are very closely linked to this storm surge because they bring extreme weather, and that can affect coastal ecosystems significantly. So we have NDEM, that is National Database for Emergency Management, managed by NRSC and ISRO. It provides you the storm surge information. So this is the eastern coast, you can see, The legends are also given, that what is the storm center and how it moves. So all this information is provided here. So to conclude, what are the key takeaways? So we have understood that how various hydroclimatic measurements are recorded, in what different formats they are recorded, and what are and in what forms they are disseminated. Now, why they are important? They are crucial for hydrologic modeling, flood and drought analysis, water resource planning, climate change impact assessments. So they are making them vital for your environmental resource management. Also, we have remote sensing and reanalysis data products, which provide long-term consistent observations at a very finer spatial and temporal resolution. So they can fill in for missing ground-based observations and make our assessments more reliable. So here's an activity for you, that based on the lectures, based on this lecture, compile a list of data sets and their sources involving at least 4 in each category. So for in situ data set, let us say you have precipitation data set, so it comes from IMD. Then you can have temperature data set, it again comes from IMD. So like that, these are the in situ data sets. For remotely sensed data sets, again you have TRMM, that is one source, it provides precipitation. Then can be other source which provides couple of more data sets. So like that, compile a list with their sources, and that would collate a wonderful information at your end. These are few reference materials which can be used. So thank you for your attention, and we will discuss next, that is how to derive extreme rainfall and temperature indices using this gridded data, and in particular, but we can use for the other data as well. Thank you so much. We'll meet next time.